So this is the idea of implicit differentiation, and a function implicitly just means that it's written so that it's not solved for one variable in terms of just the other variable. So in terms of y and x, it would mean it has x's and y's on either or even both sides of the equation. So it's not y equals something just in terms of x. Okay. So if I take this relation x squared plus y squared equals 4, that's a circle with radius 2. So circle radius 2. And if I were to solve that circle equation, it would give me these two different representations of the top half. That's this one here. And then the bottom half is this one here. And I could find the derivative of those separately using the chain rule, and then plug in any x coordinate and get my slope of the tangent line at that point. Okay. But what happens is that with certain relations, and relations are like the ellipses, hyperbolas, sideways parabolas, circles, it's easier or only possible to do it implicitly. Okay. And so this is the implicit representation of this function. And I'm going to show you how to do that implicitly in a minute. So it's based on the chain rule. So what we're thinking of here is like every time you have an x term, if you're differentiating with respect to x, you don't have to worry about the chain rule. But every time you have a y term, or let's say an independent variable, it could actually be a function in terms of x. And so we're going to attach a dy dx to it if we do that. So it looks like this. Sometimes we're going to go ahead and solve this one explicitly first, and so we'll have an answer, and then we'll do it implicitly and get the same thing. Okay. So this one, if I move the 2i or divide by 2 first, and then y equals 2x squared minus 6. So dy dx would equal 4x. So dy dx would be 4x. So I'm going to demonstrate that we'll get the same thing doing it implicitly. So here's the step process. So because of the chain rule, every time we take the derivative of y and treat it like a variable x, we're going to attach a dy dx to it. So to differentiate both sides, it's just like the rules of equality for algebra. We've got to differentiate each piece on both sides. The derivative of 4x squared would be 8x. And if I were to attach something, I would attach a dx dx, but that's equal to 1. So I don't need to do that. And then minus 2 dy dx, and then equals the derivative of 6 is just 0. That's the first step. And then we collect all the y prime or dy dx terms onto one side. So this one we can erase. This one's not really here. We've got one dy dx term. We're going to keep that on the left-hand side. And then move the 8x over. So everything that doesn't have a dy dx, we just move it to the other side. Keep all the dy dx's together, and oftentimes you'll have to factor out a dy dx. In this case, we don't. So there's only one of them. So factor out a dy dx or solve for dy dx. So by dividing each side, we get dy dx equals negative 8 divided by negative 2 is positive 4x. Same thing we got up here. So they are equivalent, at least in that case. So But those are the 4 steps.
And then you would do.
It's a little more complicated one, but it's not too bad. There'll be more dy dx terms. So it's y to the 4th plus 3y minus 4x cubed equals 5x minus 1. The beauty of implicit is we can do a derivative just piece by piece, which is nice. So derivative of y to the 4th would be 4 y to the 3rd dy dx. And then plus the derivative of this is 3 dy dx. And then minus 12x equals 5, and the derivative of 1 is 0, so that exits out these piece. Every time I take the derivative of these y terms, I'm attaching a dy dx. And then those will all stay on the left, and these will all move over to the right. So I have 12x plus 5 over here, and 4y cubed dy dx plus 3 dy dx over here. Then I factor out the dy dx. And then finally just divide through by that term in parentheses there. So dy dx equals 12x plus 5 divided by 4y cubed plus 3. And that's my derivative in implicit form. It's in implicit form. Has x's and y's on it. So if I want to find the slope of the tangent line at 1, -2, I'm just evaluating dy dx not at just x, but at x and y. And so I'm plugging in a 1 for x and a -2 for y, and I get 17 over -29 is my slope of the tangent line at 1, -2 for that relation. That's it. So they do have some in the textbook where they ask you to plug in a point or set it equal to a slope or write the equation of the tangent normal lines. But you're just plugging in an x and a y instead of just an x to get the slope. So here's one. This was the one we did earlier. X squared plus y squared equals 4. We did this one, but we're going to find the second derivative of this thing. So x squared, this is our circle function. We're going to start by finding the first derivative, which is 2x plus 2y dy dx equals 0. And if I subtract the 2x over, divide by 2y, I get dy dx equals -x over y as my derivative for that circle relation. So then I can plug in any coordinate on the circle and it would give me the slope of the tangent line. Second derivative, here's how it works. It's d2y dx2, and I've got to use the quotient rule on this guy. So derivative of the top would be -1 times the bottom, y, minus derivative of the bottom is 1 dy dx times the top, -x, all over the bottom squared. So it's quotient rule, but when I take the derivative of y, I've got to attach a dy dx when I'm doing this implicitly. And this is about done, except that we would take this dy dx and substitute in the first derivative up here, right there, and then we're good to go. So second derivative is -y plus x, and I'm going to replace dy dx with -x over y all over y squared. And on a multiple choice, AP multiple choice question, they might simplify that a bit. You have to be prepared to do that. But for our purposes, this is the second derivative implicitly, and you're good to go. So that was it. I gave them a couple examples to try. If you want to try them, you can. You're going to have plenty to try. But here are solutions to each of these implicitly if you want to try them and then match them up. Or you can just go work on the bookwork and try those too. But you just need to be able to do these. Lots of different variations of this.